So we're looking at doubly reinforced concrete beams. When you watch this video, you should probably have a copy of AS 3600, which is the Australian concrete standard. This is one that you probably want to print out and keep a copy of yourself. You'll use it a lot in your engineering life. I'm also going to refer to the textbook, which is the one online by Beletich, Argeo, and Paul Uno. That's chapter 2, and actually chapter 5 is the one you want, doubly reinforced concrete beams, which I'll refer to as well. Okay, first we'll go back though and cover the basics of concrete beam design. When you have a concrete beams, for the sake of argument in this tutorial, we're going to assume that our beam is a beam under gravity load like that, so it bends down like that, okay? So when I say the bottom of the beam, I'm talking about the tension side. When I say the top of the beam, I'm talking about the top. If it's a cantilever, the whole thing gets flipped upside down, okay? But for this tutorial, we'll be assuming all our beams are like that. We'll be assuming all our beams are rectangular, okay? We'll talk about T-beams and other things a bit later. So in a concrete beam, when that's in bending like that beam, you guys know that in bending, the top is in compression and the bottom is in tension, okay? If that's not clear, there's a topic on that fairly early on. And you know that concrete does pretty well in compression, so all that face goes into compression and the tension is held by the steel here, okay? And concrete has very little tension capacity, so it's there, but it doesn't really work for you. So what I'm going to do is take a slice of that beam, look at it around the other side. So if we take a narrow slice of beam like this, okay, there's our beam, it's that deep. And we're going to have steel right at the bottom here. That's a tensile steel. And the rest is concrete. So we're going to assume no top steel at the moment, okay? This is the top surface of our beam. And this is a slice. And we're going to go through and look at the different things. So if I draw the neutral axis of the beam, it goes through there somewhere. And the steel is here. So that dimension is a small d. From the top of the beam to where the steel is, central of the steel, okay? The whole thing is big D, all right? And if we look at the strain of this, so the strain is how much the beam stretches. When it bends, you get a straight line going from the bottom to the top. That's a straight line. That's one of the assumptions of bending theory, is that strain is linear. So you get maximum strain at the outside edges, and you get no strain at the neutral axis. Okay? Is this all making sense so far? All right. Now, concrete has a stress-strain diagram. Now let's do steel first. Steel has a very convenient stress-strain diagram. It goes up, and then it yields and it's flat. Okay? In reality, it actually does a bit of this and a bit of that, and then kind of goes like that. But for engineering terms, we assume that it goes up to its yield strength, and then it holds that force at the yield strength, okay, for quite a large strain until it fractures. All right. So so that's steel. Concrete has a very different shape. Concrete is unfortunately inconvenient, and it has a shape a bit like this. Okay. So it's linear at first for the small bit, and then it curves off. So this is stress. This is strain. So in this axis, we've got how much are you pushing on the concrete. In this axis, we've got how much is the concrete actually stretching or compressing. Okay? And the slope of that line is called the elastic modulus of elasticity. Okay? If that's 20 MPa concrete, 30 MPa concrete has a slightly different shape. 50 MPa concrete has a slightly different shape. 80 MPa concrete has a slightly different shape. All right, and what that means is that when we go over to here, if we draw, that's our strain, if we draw our stress diagram, so because the neutral axis, nothing's happening, the material at the neutral axis is not stressed, the material at the extreme fibers is highly stressed. So we're going to put a force here. If this rectangular beam was, say, made of rubber, we would have equal tension and compression, and it would look like that. Maximum tension here, maximum compression there, and increasing tension and compression as you go away from the neutral axis. Okay? However, we don't have that. Our concrete cracks at assuming zero stress, so we don't get any tension. We only get tension from the steel, and that's all down here. So I put a big arrow there for our tension force for our steel bars. Okay? Here's the beam over here, just to remind you. It looks like that. It's got a couple of steel bars in the bottom. And the compression force for the concrete would actually look a little bit like that shape. Now this is the beam when it's working as hard as it can. There's the neutral axis. The distance to the neutral axis is Ku times D. There's the D, so Ku is a number less than 1. Ku is a proportion of D. That tells us where the neutral axis is. Now, when we do theory of bending, we know that the tension force and the compression force are equal. Okay? The area of the steel times the stress in there is the force. The area of that concrete, there's the concrete in compression, that much, times the force, times the stress gives us the force. Now we know steel is much stronger than concrete, right? Steel has a yield, reinforcing steel has a yield of 500 MPa. Concrete has a yield of, or strength of, whatever you mix it at, say 32 MPa. 500 compared to 32, you need a much larger area of concrete to equalize that force. So that's why you've got this relatively small area of steel, big area of concrete. Okay? Now, the thing about analyzing that shape, to work out the bending capacity of the beam, we've got to take the moments of that force around the neutral axis. So here it's pretty easy. It's force times that lever arm. Here you've got to integrate that curve. Find the centroid, take that. That's a real pain in the rear, so we don't do it. Okay? We make a simplifying assumption, which is we say, let's call a rectangular stress block like that. That's all compression. And we shape that rectangular stress block so it's the same amount of force as that curve there. And then we pretend that the force really is that rectangle. And that is much easier to analyze. So we've simplified the problem a little bit. Okay? And the dimensions of that are alpha 2 times F dash C. F dash C is the strength of our concrete, so 32 MPa. Alpha 2 is a number less than 1, so it's a proportion of our strength of concrete. And the height is not all the way down to the neutral axis. It is gamma times Ku times D. So gamma is another number which is less than 1. Okay? So to summarize where we're at, this is all in the singly reinforced beam topic. To summarize where we're at, then we've got, I hope you'll forgive me that those arrows both go the wrong way. Let's do tension like that if you like. So they're going opposite directions. The bending moment capacity of our beam is that force times the lever arm distance plus that force times the lever arm distance. Okay? That's how singly reinforced concrete beams work. And when you do the numbers, alpha 2 comes from the code. It comes from clause 8.1.3, and it's got a little formula in there. The formula is different whether you're talking about the current version of the code or the previous 2009 version. But clause 8.1.3 has it, and it's about 0.85. And gamma also has an equation. It depends on the strength of the concrete because of these different shaped curves. And gamma is approximately between 0.67 and 0.92. And that's also in clause 8.1.3. So far, so good? All right, what do you guys know about Ku? It's less than 1, yep. Can someone tell me what the maximum value you should design with is? Anyone? 0.36, very good, yep. Okay? In the current code, KU is not allowed to be bigger than 0.36. All right? If you under-reinforce the beam, so if this area of steel is quite small, the neutral axis is going to be quite high, KU is going to be a very small number. If you over-reinforce the beam, you pile in a whole bunch of extra steel here, KU is going to be quite large, and the beam fails in a brittle manner. Everybody dies. No one likes that. Okay? All right. Now, so that's the singly reinforced concrete beams. That's what you cover in that topic. All right? The two formulas which govern that, I'll write them up here for you, but they're in the book. Mu naught, which is the bending moment capacity of the beam, equals the area of steel in tension, which are those bars there, times FSY, which is the yielding point of the steel, which is 500 megapascals, times D, distance in concrete, times 1 minus 0.5, area of steel again, FSY, yielding point of steel again, times alpha 2, that's that value there, times B, times D, those are dimensions of the beam, times F dash C, which is the strength of the concrete. Alright? For singly reinforced beams, that's the strength of that. And remember, you have to put the phi factor in there as well. And the value of KU equals 1 over alpha 2 times gamma, that's the gamma, times the area of steel over BD times the ratio of the strength of steel over the strength of the concrete. F dash C. Okay? And the maximum is 0.36. If you don't make KU less than 3.36, the code penalizes you. Okay? That number used to be 0.4 in an earlier version of the code. It's now 0.36. Alright, so that is our singly reinforced beams. Okay? The majority of beams, you guys, sorry, feel free to interrupt with questions if you want to ask me on that. Did I do it wrong?
No.
Max is looking like I'm doing it wrong.
I was trying to read it.
Oh, okay. Okay. The vast majority of concrete beams, when you design them as singly reinforced concrete. But when you go on site and you look at concrete beams, you will find they always, or almost always, have top steel in like that, and then the rings around that go like that. Okay? So you might think, why on earth are we just talking about singly reinforced beams when actually there's always top steel? Okay. First, the rings. Anyone know what they're for? Okay. The rings, they're also called stirrups. They're to resist shear force. Okay, you'll learn about them when you get to the shear force one. But they do shear force and tension, and they hold the concrete together. Sorry, shear force and torsion. Yeah. All right, now, if you design a beam without those, and you work out its capacity, and then you add a couple of small bars there, like that, you don't really change much in the way of bending capacity. You're talking a few percentage points. Those bars often are there just to hold the rings in place. Okay? The shear rings are needed. Those bars, you need something to hang the bars on. That's what they're there for. However, if you've got a concrete beam and you've done this equation and you need more capacity than that, but you can't make the beam bigger, then now we're talking about doubly reinforced concrete beams. Okay? And that's what we're getting to today. So, remember all that. Now, a doubly reinforced concrete beam is basically a primary beam plus a steel beam. So that, all we're doing now is saying Okay, let's take top steel. Let's say we've got, in this one we had 4 bars here, 2 bars at the top. What we're going to do is imagine that is without those 2 bars, and put those 2 bars over here. So now we have a singly reinforced concrete beam plus a steel beam. Alright, there's the neutral axis, there's the neutral axis. The mu naught of that equals that equation. The mu naught of this is the area of steel. Let's go, that's the area of steel in compression, that's the area of steel in tension. Area of steel times lever. It's got a force, it's got a lever arm, there's the moment. So it's that equation plus that. We're done here, that's all it is. Okay? We're just adding a steel beam to a concrete beam and doubly reinforcing it. Okay? I'll say this again because this is the main concept we've got to get in this tutorial today. All I'm going to do after this is throw in a few complications to that. But that's the main concept. So let me try drawing that on another diagram. I'll leave that equation there. If you have a beam like that, and you have to design it for 500 kilonewton meters, and you do that equation, and the maximum, remember your Ku is a maximum of 0.36, so you just can't go adding steel, because if you keep adding steel, your Ku goes up. So when the Ku gets to 0.36, that's that beam working as hard as it can work. That's all it's going to do. And we've asked for 500, but we've only got, I don't know, 350. We have to find the extra 150 from somewhere. So what we do is we add some top steel, same amount of bottom steel. There's a lever arm between them. That plus that gives us a bigger bending moment. Does that make sense? That's all we're doing. The concrete is holding our bar up there quite nicely, so we can develop full compression there. Concrete is holding our bar there quite nicely. We can develop full tension there. And that is how doubly reinforced concrete beams work. Okay? All right. Let's start adding the complications now. Okay. The strain here, when concrete is working really hard, gets to the maximum force it's going to take, it's got a strain of 0.003. Okay? Strain has no units because it's length over length. It's 0.003 meters per meter. Every meter, it stretches 0.003, another 0.003 meters. So if you take a meter long piece of concrete, you stress it up to its maximum point, it's going to shrink, push it by maximum point, it's going to shrink 3 millimeters. Okay? That's a relatively, that number is fairly independent of the concrete strength. Okay, so there's a nice fixed point for us. Okay, let's look at steel. Steel, we know there's the stress. What was the maximum stress in steel, or the yield stress?
500.
Thank you. 500 MPa. Okay, so steel gets to 500 and then it goes flat. We want to know what that point is. Does anybody know the elastic modulus of steel, or the modulus of elasticity? 200,000 megapascals. Same units of stress. Modulus of elasticity of steel is 200,000. Okay? Aluminium's got its own number. All different materials have their own number. 200,000. So elasticity, that number is the stress over the strain. Okay? So the stress is 500. 500 over our strain equals 200,000. So our strain equals 500 divided by 200,000. What's that number? Anyone with a calculator? Is it 0.0024? 25. 0.0025. Okay? So, what I've said here is that the point at which the steel yields is 0.0025. Okay? Now, we have, let's draw on here, take off these things just to clear it up a little bit. Alright? There's our 0 line. We've got a bunch of reinforcing in the bottom, which has all yielded. Okay? If you want to know why that's the case, I can go into that later, but the bottom steel has definitely yielded. Alright, go with me on that. So the force there equals the area of the steel times 500. 500 megapascals. The area of the steel, I'm talking about literally the cross-sectional area of the steel bars you put in. Alright? Now up here we've got the force of the concrete, and we're going to add some top steel. Alright? So here we're going to have that force is going to be the area of the steel in compression, ASC, times whatever the stress is. And so the question that comes out is, has that steel yielded? Okay? We know that at this point, there's the steel there. It's not right at the top, it's buried under the concrete a little bit. We know that that's 0.003. Is that 0.0025 or not? Okay? Now on some beams the answer is yes, on other beams the answer is no. But we have to know that. So the way we work out that is just basic triangles. We need to work out what's the KU. That gives us that distance. We've got D, KU times D. That will tell us whether that dimension is over 0.0025 or under 0.0025. If it's over, the problem is simple. The stress in the steel is 500. If it's under, then it's proportionately less than 500, whatever it is. Okay. Now there's a formula in that textbook about the depth to that steel versus the depth to that steel minus this minus that. But basically, all it's doing is using triangles, looking at the geometry and saying, has that yielded or not? Okay. So that's the first complication. If it hasn't yielded, then this lever arm here, that's going to be less force than that one, so it's out of balance. So we have to adjust the beam for that. Okay? All right, any questions so far? Okay. Okay, the next complication. We've got steel there, and we've taken it out and using it for the steel beam. This is our primary beam, this is our secondary beam. Okay? That steel actually was taking up area of concrete. And although it seems quite small, it is significant enough to matter. Because there, concrete is missing a bit of area which is occupied by the steel. Okay? So we have to deal with that. The difficult way to deal with that would be to say, all right, what's the new area of this concrete? What's the new centroid? What's the new distance? And that just sounds like torture, so we're not going to do that. The way we do it is to say, all right, let's pretend that the amount of force that, if that steel bar was concrete, let's pretend the bar's not there and pretend it's just concrete, and let's deduct that same amount of stress from here. So if that was 32 MPa concrete, we take 32 megapascals away from our force there. Does that make sense? Because we can't use the force twice. So we're saying, yeah, whatever that force is, whatever that stress is, we're taking 32 megapascals of stress away from it. Okay? The maximum that could have been was 500. If it was 32 MPa concrete, 500 minus 32 is 468. Okay? Now, when I said the F-C, it's actually not the F-C, it's the alpha 2 F-C, that value. Okay? So the stress we're going to use in the bottom steel is stress yield, and the stress we're going to use in the top steel is stress, whatever it is based on the strain, minus the stress of the concrete. And that is alpha 2 F dash C. So that's how the concrete strength sneaks its way into the equations for the steel beam. Okay? Alright, that's all the complications there are. So let's try and do an example if we can. No, sorry, I'll talk you through methodology first.